Hello. I'm going to record a short video on an introduction to magnetostatics and conservation of charge, which sort of fills in a gap between lecture notes 12 and 13 on current and the Biot-Savart law. Let's talk about it. So the first thing is to define what magnetostatics is about. And just like electrostatics was dealing with stationary charges, magnetostatics is dealing with the magnetic fields that are produced by steady currents. And the point of this lecture is to define what a steady current means. And so you know lots of examples of steady currents, like for example, here's a loop of current. And as long as that current doesn't change in time, that's a steady current. And you could have an infinite wire carrying a steady current. But you can't have a finite wire. So a wire with endpoints carrying a current, that's a possible situation, but it's not a steady current, even if I is constant in time. And so I want to talk about why that is. The reason has to do with conservation of charge, which is also called the continuity equation, which we'll see why in a moment. What does charge have to do with it? Sorry, my stylus isn't working very well. So let's look at that finite length of wire. So it's a wire that has an endpoint. There's current flowing along it. And what's happening is as that current flows, that charge has to go somewhere. And it has to build up at the end of the wire. And there's some increase in the amount of charge that's there. We know that has to be the case because charge is conserved. You can't create or destroy charge. And so the fact that charges are moving around and they don't disappear means that if you have a current that just ends, there's charges going to be building up in that region. And it turns out that that changing charge distribution is enough to invalidate magnetostatics. Even though the equations don't have Q's in them, they have I's in them, having a non-constant charge distribution is enough to invalidate magnetostatics. And so we have to restrict ourselves to only talking about currents that don't do this. So how do we decide? We can try to calculate what is that dq dt. So we're going to ask, what is dq dt in some volume? So here is our specified volume V. What's dq dt for the charge inside that volume? Well, by conservation of charge, it is the flux of current entering S, the surface of that volume. What does that mean in equation form? Well, we have some surface integral that we have to do. So we're going to have an integral something dot dA over that surface. How do we know how much charge per unit area is entering per unit time? That's a current density. In particular, it's the volume current density. And so in lecture notes 12 on current, we saw how to compute a current I. So the left-hand side of this has units of normal current. And so this also has to have units of normal current. And so it's going to be a surface integral of the volume current density J. Except there's a problem, which is that this equation as it is dq dt is the flux of the current leaving S. And that's because that points outward. dA points outward. So we have to throw in a minus sign. So dq dt inside a volume is equal to minus the flux of J through the boundary of that region. And that is the equation version of conservation of charge. That's not quite the continuity equation. What I'm going to do is say, well, there's another way to think about dq dt, and it's the time derivative of the total charge in that volume, which is a volume integral of rho d tau. Okay. And now we're about to have something interesting. So I'm going to start a new slide. There should be a way to insert a new slide, but I don't know how to do it. Huh, fancy, okay. Well, we're not there yet, hang on. We'll come back to this. So we had from the last slide, ddt integral over the volume of rho d tau. So that's how is the total charge in that volume changing, is minus the flux of the current through that surface. So integral j dot dA is how much current leaves the surface, is how much charge leaves the surface per unit time. And minus that is how much charge is entering the surface per unit time. So I can pull that derivative inside because that's not a derivative over the region, it's a derivative of with respect to time, which is not what I'm integrating over. So it's become a partial time derivative, d tau. Then I'm going to apply my favorite theorem, one of my favorite theorems, to make this surface integral into a volume integral of minus the divergence of J. And then we say the magic words that, well, this equation is not just true for the volume I picked, it's true for any volume. Charge has to be conserved everywhere. And so then this becomes a differential equation that has to be true. The partial derivative of rho with respect to time has to be equal to the negative divergence of J. And that is the continuity equation as a normal difference. Okay, so one more slide. If you remember one thing about magnetostatics, it's this rule. It's electrostatics, but everything becomes cross products. All divergences become curls, all dots become crosses, and some normal multiplications become cross products as well. And so we want to build a Biot-Savart law. How do I compute the magnetic field at a point R by integrating over a current? And I'm going to do it by analogy to Coulomb's law. I'm going to do it for volume currents, but it works the same for surface currents or line currents. It's just that the analogy is the most clear there. So I'm going to say, okay, well, I have my 1/4 pi epsilon naught. I'm integrating over all of space where there's charge. I have my rho of r prime. I have my script r hat over script r squared d tau prime. So what's my analogy going to be? Well, the thing creating the magnetic field is a current. So in my integral, I'm going to be integrating j of r prime instead of rho of r prime. My constants are different. You probably know that I use a mu naught instead of an epsilon naught, and the mu naught goes in the numerator just to be confusing. So I get a mu naught over 4 pi. I have my j of r. I'm going to still have my d tau prime, so I'm still integrating over all the places where there's current. But how do I include the directionality and the 1/r squared? Well, I have a vector. I have to include this other vector, r hat over r squared, and I have to get a vector. There's only one way to do it. I insert a cross product. So that's a guess based on an analogy, and it turns out to be the right guess. You can figure out how to relate j d tau prime to k dA prime and I dL prime. And remember, with line currents, you can put that vector arrow in either place, either over the dL or over the I. I usually put it over the DL. And that basically is the starting point. Everything else is going to follow from here. That's about it.